Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the 4 to 20 milliampere standard and we will see that why it is the preferred standard in the industrial environment. So this 4 to 20 milliampere standard is the analog signal transmission standard which is used in the industrial automation and the process control to transmit the field information from the sensors to the control system like the PLC. And this information is transmitted in the form of current. So let us understand why it is the preferred over the other techniques of the transmission. So in the industrial environment, different types of sensors are used to measure the various process parameters like the temperature flow and the level. Now these sensors can transmit the data from the field to the PLC either in the form of voltage or the current. So when the sensors transmit in the form of voltage, then typically this voltage is in the range of 0 to 10 volt. So to transmit this data along with the sensor, there is always a transmitter. So this transmitter reads the sensor data and converts it into the appropriate range for the transmission. Now as you know, this industrial environment is electrically noisy due to the various machineries like the motor, variable frequency drive and the high power cables. So when the sensor data is transmitted in the form of voltage, then due to this electrical noise, this voltage signal is susceptible to the EMI. So this electromagnetic interference can induce a small voltage in the signal wire and this small voltage can corrupt the measurement. For example, let's say the transmitter is sending the 5 volt signal. But due to this noise or this EMI, the receiver in the control room receives the 5.1 volt. And sometimes this change in this voltage can cause the problem. So in short, in this industrial environment, this voltage signal is susceptible to the noise. While if you see the current signal, then it is immune to the noise. So that is one of the advantage of transmitting the signal data in the form of current. Now the another drawback of the transmitting the sensor data in the form of voltage is that as the voltage signal propagates over the cable length, then the voltage signal gets attenuated because this cable has some finite resistance. And many times this cable length varies from hundreds of meters to the several kilometers. So in that case, due to the higher resistance, there will be a voltage drop when the signal travels from one end to the another end. So it is quite possible that the transmitter is transmitting the 5.2 volt, but by the time receiver receives that signal at the other end, then the signal drops to the 5 volt. So that is the issue with transmitting the voltage signal over the long range. But if you see the current signal, then that is not the problem because the current remains same throughout the cable length. So that is another advantage of transmitting the field parameters in the form of current. That means using this 4 to 20 milliampere signal, it is possible to transmit the signal over the longer distance. Now if you see the another advantage of this standard, then this standard has the concept of live zero. That means here the 4 milliampere represents the lowest value or the 0% of the full scale value. For example, if the temperature sensor range is from 25 degrees Celsius to the 100 degrees Celsius, then this 25 degree represents the 0% of the full scale range. While if you see the 100 degree, then that represents the 100% of the full scale range. That means here in this 4 to 20 milliampere signal, the 0% of the measurement value is the 4 milliampere. But instead of the 4 milliampere, suppose the minimum value of the measurement range is kept 0 milliampere, then in that case, the 0% of the measurement value corresponds to 0 milliampere. And in that case, suppose there is a fault in the loop or if there is a device failure or the broken wire, then we do not know whether it is due to the fault or due to the actual 0% of the measurement value. That means instead of the 4 to 20 milliampere, suppose the range is kept from 0 to 20 milliampere, then in that case, the fault finding becomes difficult. But in case of the 4 to 20 milliampere standard, as the minimum signal is 4 milliampere, so whenever the signal is equal to 4 milliampere, then we know that the link is live and the measurement value is indeed a 0% of the full scale range. So that is the live zero concept. That means the value of the 0% measurement is higher than the 0 milliampere. And whenever the signal level drops below the 4 milliampere, or if it becomes the 0 milliampere, then we know that there is some fault in the loop, like the broken wire or the device failure. So in this way, using the 4 to 20 milliampere standard, it becomes easy to identify the fault condition. Now why this specific range is only kept, we will discuss it little later. But that is another advantage of 4 to 20 milliampere standard. That means because of the live zero, the fault finding becomes easier. So if you see this 4 to 20 milliampere standard, then it is the two wire loop. That means on these two wires, the signal current is flowing between the transmitter and the receiver. Now the advantage of this method is that using the same two wires, it is also possible to power up the transmitter. So nowadays, the receiver themselves are capable of powering this 4 to 20 milliampere loop. That means they have the separate power to power up this loop. So typically, they provide the standard 24 volt voltage. And of course, over the loop, there will be some finite voltage drop. But still, even after the voltage drop, the sufficient voltage will reach to the transmitter. So using this voltage and the current that is as low as the 4 milliampere, it is possible to power up the circuitry inside the transmitter. So for example, let's say the sensor output of this flow meter corresponds to 8 milliampere. That means in that case, the transmitter needs to send the 8 milliampere current to the receiver side. So what this transmitter will do, it will draw the 8 milliampere current from the power supply. And from this current itself, it will power up all the circuitry inside the transmitter. And then the same current will return through the loop. So now on the receiver end, there will be a 250 ohm resistor, and through this resistor, this 8 milliampere current will pass. So due to that, there will be a voltage drop across it, and the ADC inside the receiver will read this voltage. And in this way, this 4 to 20 milliampere current will get converted into the voltage at the receiver end. So the point is, in this 4 to 20 milliampere loop, using the same signal current, it is possible to power up the transmitter. And therefore, these transmitters are known as the loop powered device. That means they can get powered up using the loop itself. Now if the receiver does not have the capability to power up the loop, then in that case, this is how the loop is powered. So once again, the power supply will provide the 24 volt supply to the loop, and the transmitter will draw the current from the power supply based on the sensor output. Let's say that is equal to 8 milliampere. So the same 8 milliampere current will go through the return wire. So now the receiver senses that current and converts that current into the voltage. So as I said, inside the receiver, we have the 250 ohm resistor and the ADC. Or equivalently, this is how it can be represented. So when the current passes through this 250 ohm resistor, then there will be a drop across it, and this ADC reads that voltage drop. So as you can see, the readout mechanism in this 4 to 20 milliampere loop is also very simple. Now the another advantage of this 4 to 20 milliampere standard is that using the same two wire loop, it is also possible to transmit the digital signal on top of the analog current signal. That means using the same two wires, it is also possible to perform the digital communication. And for that, the transmitter and the receiver should also support the communication protocol. So typically, this digital communication is carried out over the hard protocol. That means for that, the transmitter and the receiver should also be hard enabled. So as per this protocol, the digital signal is superimposed on top of the analog signal using the frequency shift keying. So as per this protocol, the logic 0 is transmitted using the 2200 Hz sine wave, while the logic 1 is transmitted by the 1200 Hz sine wave. And of course, this frequency shift keyed signal is also a current signal. That means this 1 milliampere peak-to-peak current signal is superimposed on top of the 4 to 20 milliampere signal. And at the receiver, both digital and the analog signals are separated, and both of them can be treated separately. So in such case, if you have the heart enabled device like the handheld communicator, then it can listen to these digital signals, and remotely it can configure the transmitter, or it can also perform the required calibration. So that is another advantage of this 4 to 20 mA standard. That means using this, it is also possible to transmit the digital signals using the same two-wire loop. So now, let us understand why the specific range of 4 to 20 mA is selected for the transmission. So we have already seen the concept of the live zero. So we have seen that instead of selecting the 0 mA, if you select the 4 mA for the minimum measured value, then the fault detection becomes very easy. But then the question is, why it is only 4 mA? Because it could have been also 2 mA or the 3 mA, right? So the reason is that this current is also used to power up the transmitter. And earlier, we have already seen that. So initially, the 1 mA or the 2 mA current was also considered as the minimum current. But at that time, that current was not sufficient to power up the electronics of the transmitter. And that is why the 4 mA current was selected as the minimum current. So this 4 mA current was enough to power the vast majority of the transmitters and operate them reliably. So that is the reason for selecting the 4 mA as the minimum current. But then the question arises, why only 20 mA was selected as the upper range? So the reason is that before the electronic instrumentation became dominant, the industrial plants were running on the pneumatic signal, and the established standard for the pneumatic control was between the 3 psi to 15 psi. So at that time, the 3 psi was the live zero. That means if the pressure drops to the 0 psi, then the engineer or the technician knew that there is a leak in the airline. And similarly, the 15 psi pressure was the 100% signal. So when the equivalent electronic standard were being developed at that time, the engineers wanted to create the system that is analogous to the pneumatic system, because the technicians and the engineers at that time were already familiar with the pneumatic system. So if you see the ratio in the pneumatic system between the maximum and the minimum value, then that is the 5. So the same ratio was also maintained in the new standard. So that is why the range in this standard is from 4 to 20 mA. Now another reason for selecting the 20 mA current as the maximum current is that this current is intrinsically safe to avoid the hazard. So by capping the maximum current at the 20 mA, it is much easier and the cheaper to design the circuits that are intrinsically safe. And also for the human safety perspective also, this current is in the safe range. So that is the reason for keeping the 4 to 20 mA range for this standard. So in a summary, these are the advantages of the 4 to 20 mA standard. So I hope in this video you understood why the 4 to 20 mA standard is preferred in the industrial automation and why this specific range is selected for this standard. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.